All right, here we are. I'm probably still in Brazil at this point, and this is the second time I've done this. The first time I ran through it, I just checked the video and it wasn't very good, so I'm going to try it again. Anyway, today we're going to talk about limiting reagent. While I was away, you did a lab with Lego, and you hopefully learned that depending on the number of pieces you have, you're limited by the number of cars or objects that you can make. For instance, if you only have 6 wheels, you can only make one of those beach buggies that you were making during the exercise. Okay, so that was a couple days ago. So now we're going to look at a couple more analogies really quickly, and then a chemical example, and how to figure out these things. This is an important concept, especially in industry. You always want to know how much product that you theoretically can get out of a certain amount of reagent. You don't always get that. We'll talk about that next day. But you always want to know how much you can get, and it's very rare that you would have stoichiometric or exactly the right number of molecules of each thing to react. In addition, there are certain advantages to making one reagent in excess, because it helps to in cases of equilibrium, which we'll study next year, to maximize yields. Okay, so looking around the classroom, if you're in the classroom, if you're not, I know a lot of students might be away. If we were going to have a dance and just with our class, and we had one rule that we could only have heterogeneous couples, one boy plus one girl gives one couple, that's our equation. How many couples could we have? What's the maximum number of couples that we could have? And I'm not there, so I can't tell you what that is. I don't know who's shown up. However, you should be able to figure that out fairly easily. How many couples? Just look around. You can stop the tape if you want. And the other thing I ask is how many wallflowers? What gender are they? Like, who would be standing along the wall with nobody to dance with? That would be me in high school, just so you know. Standing along, hoping somebody would be able to dance with me, but very often not so good. Anyway. So what limits the number of couples? Is it the boys? Is it the girls? You can tell me. The definition for limiting reagent and excess reagents are there in the middle of the page. I'm not going to go over them. You can read them just as well as I can. This is on page 151, by the way, of your notes, so you should be on there. And then I just provided one more, an old Corel draw. If I have 3 bike frames and 4 wheels, this is very similar to what we did in the lab. How many bikes can you get? Well, obviously you can only get 2 bikes, and you're going to have a frame left over. Okay, let's look at a chemical example right now. Here we have ammonia plus hydrogen chloride reacting to form ammonium chloride. You're given 1 gram of each of your 2 reagents, and that's the key to knowing it's a limiting reagent problem. There are 2 reagents, masses given. Okay, so as soon as you see that, I shouldn't have to tell you that it's a limiting reagent problem. You should know from the fact that you're given both masses. So make note of that. And make sure that your reaction is balanced. Okay, I'm not always going to balance that for you. This one, in this case, it is. You'll notice that I'm copying it in 2 different colors. The coefficients in 2 different colors. There's a reason for that, and I'll get to that in a minute. You don't have to do that. I'm just going to show you where certain things come from. First thing that we're going to do is determine the number of moles of each reagent that we have. You've done this a bazillion times before. So hopefully you're well practiced at it now. So let's take 1 gram of ammonia times 1 mole of ammonia over 17.0 grams of ammonia. And that equals to 0.0588 moles. Okay, and then we have also 1 gram of hydrogen chloride. Notice I'm saying hydrogen chloride because it's a gas instead of hydrochloric acid. 1 mole of hydrogen chloride over 36.45 grams of hydrogen chloride, and that works out to be 0.0274 moles of HCl. So now how do we figure out, which one is limiting? There are 2 different ways. I personally like this because I think it teaches better for understanding. Pick one of these. I'm just going to pick the top one, but you could pick the other one if you wanted. I didn't want to do that, sorry. I want to take the number of moles of NH3, and I'm going to find out how much of the other one I need. So Sorry, I'm trying to rush because I've just done this. HCl, I know I have 1 mole of HCl for every 1 mole of ammonia. They're going to cancel. It tells me I need 0.0588 moles of HCl. Do I have it? No, I don't. Okay, so I only have 0.0274 moles of HCl, so that makes this my limiting reagent. Okay, so there is another way of doing it, and I'm not going to fill in the space down here, but I said find the limiting reagent using the easy way, and I do call it the easy way. If I take the coefficient that's in the balanced equation and divide the number of moles of that entity by the coefficient, and I'm going to get here 0.0588, and notice that now the reason I chose different colors is because they're both number ones, and I just wanted you to know where those came from. I'm going to get the same number here, 0.0274, and whichever one is lowest is the limiting reagent. So notice that we come up, we're completely consistent here. We get the same answer. And the IB, as far as I know, will allow that very simple thing. It's a little bit back of an envelope type of thing, but it works all the time, and I don't mind if you want to use it. I do think this teaches a little bit better for understanding, however. Okay, and then what do you do in the end? Well, you find the amount of the product using our standard mole method. Whoops, I'm not going to use red on this. So we take the limiting reagent, and that's the key. You only use the limiting reagent on this one. I get a lot of students that use the wrong one. So you take 0.0274, and by the way, it's what you've calculated here, not the number that it went once it's divided by the coefficient. So I have that many moles of hydrogen chloride. I know that I get 1 mole of ammonium chloride for every 1 mole of hydrogen chloride, and I know, or I've calculated that the mass of ammonium chloride is 53.49 grams. I hope I'm right. You can check my math. Like I said, I'm kind of in a hurry here. I got to get on a plane soon. Anyway, it's 1.47 grams of ammonium chloride. And what I would do with this number is it reasonable? For instance, if I got 14 grams, would that be reasonable? No, only 2 grams went in. So this is reasonable. I have 2 grams that went in, I got 1.47 grams out, and obviously there's some excess material there, and that's the ammonia is in excess. Okay, let's do a slightly different example here. This is a little more complicated. This is on page 153 of your notes. Nitrogen gas can be prepared by passing gaseous ammonia over solid copper 2 oxide. You can read it. We'll go through this. Now, I've said step 1, determine the moles of each reagent. Great idea, but I would have another step 1 perhaps. Here's what I would do. I'd determine the balanced equation, okay? So, we're taking gaseous ammonia, so NH3, and seeing as they've specified the state, let's put them in, plus solid copper 2 oxide, reacts to form nitrogen, which is a gas, plus copper, which we'll say is solid, plus H2O, which will give it a gas. Okay. Now we have to balance, all right? So I know I've got 2 nitrogens there. I need 2 here. That gives me 6 hydrogens. So I'll have 3 waters. I need 3 oxygens. There's 3 oxygens. There's 3 coppers, okay? Now, yeah, okay, notice. So I'm going to put 2 there, 3 there. I should have done them in color again, I suppose. Okay, determine the number of moles of each reagent. Well, I have 9.0 grams of ammonia. We just did this one. 1 mole over 17.0 grams. And when I did that, I got a number of 0.0588 moles of ammonia. Sorry, it is not that. Oh, I've taken the wrong question. It doesn't even make sense. I knew it didn't make sense. Okay, my mistake again. Okay, 0.529 moles of ammonia. Okay, and when I take 45.4 grams of copper 2 oxide, I'm going to multiply that by 1 mole over 79.54 grams of CuO, and that's going to equal 0.529 0.573. Sorry, 0.570 moles of CuO. Okay, are we good with that? Now, determine which is limiting. Again, just choose one of them. You can choose whichever one you want. I'll choose the ammonia again. So I've got 0.529 moles of ammonia. And I know that I have to have 3 moles of copper 2 oxide for every 2 moles of ammonia. And when I work that out, I get 0.794 moles of copper 2 oxide. Well, if I compare that with this, you'll notice I don't have that much, so that makes this limiting. Once again, I can take my coefficient in my balanced equation. I can divide through by that coefficient. And I'll take the 3 here for the copper, and you're going to see that this is going to be the smaller number. So again, we're completely consistent. Once again, I don't care which one you use. Okay. All right, let's find our final mass then. Okay, so I'm going to choose my limiting reagent, and it's going to be this number. All right, so 0.570 moles of copper 2 oxide times 1 mole of nitrogen, which is what I'm looking for. There's 3 moles of copper oxide for every 1 mole of nitrogen, and then there's 28 grams of nitrogen in 1 mole of nitrogen. Okay. Cancel, 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 and we get 5.32 grams. Okay, that's all there is to it. Some students, I don't know, it's a little bit like taking a sledgehammer to a fly. We'll take both starting masses and calculate the whole thing through. You know, it takes a little longer. It doesn't take a lot longer, but it does take longer. You know, you can do it that way, and certainly you're going to get the right answer. You just choose the lowest mass at the end. However, I'd like you to show a little bit more elegance that way. Here's one that you can do at your desks. And then if you look on the next page, there are some problems here. There's some fairly simple ones that you can probably work out in your head to start with. And then questions 3 to 6 are fairly straightforward. I know I usually make them a lot harder as you go along, but these ones are fairly straightforward. So good luck with those, and if I'm in, we'll take them up next day. If I'm still in Brazil, you'll have to take another lesson first, and then we'll take them up on a future date. Okay? Thanks a lot. Bye-bye.